Question number 46. Gate 2001. 2 marks question. During orthogonal cutting of mild steel with the rake angle of the tool 10 degrees, the chip thickness ratio was obtained as 0.4. The shear angle evaluated from this data is. Answers he has given is A 6.53. First we'll write problem given data. During orthogonal cutting, mild steel, rake angle 10 degrees, chip thickness ratio equal to 0.4, shear angle pi equal to dash. So rake angle is alpha and chip thickness ratio is R. We know there is one formula to calculate it. Okay, options A is 6.53, B is 20.22, C is 22.94, D is 50. We know tan phi equal to R cos alpha by 1 minus R sin alpha. Substitute here. We need to calculate pi and pi. R is 0.4 cos 10 degrees by 1 minus 0.4 sin 10 degrees. Substitute the values. Pi equal to tan inverse 0.4 cos 10 by 1 minus 0.4 sin 10. So this is a simplification, very simple. 2 marks you can get in 30 seconds, even though the question is 3 minutes question. We can solve it. So the pi value is 22.94 degrees. So answer for this problem is C. Next question number 44 second. 44 we will do it after discussing few topics. 43. So question number 43, gate 2002. Here the question is, a build-up edge is formed while machining. So he is asking build-up edge is formed while machining option A is ductile materials at high speed, option B is ductile materials at low speed, option C is brittle materials at high speed, option D is brittle materials at low speed. So built-up edge will form only with ductile materials, that we know. So you can eliminate option C and D. Next option is, I write, shall I? While machining, so ductile materials only, either A or B. So built up edge is formed. So we know that built up edge is formed only with ductile materials. So option A, either option A or B we have to select. So if you go at high speed, the built up edge is because due to microparticles sticking to the rake face, and at high temperatures it welded to the rake face. So when you use at slow speed, then only they will have time to stay there. So answer is, while machining ductile materials, at low speed. Answer is B. Next question number 42. Gate 2002. The hardness of the grinding wheel is determined by option A is hardness of the abrasive grains, option B is ability of the bond to retain abrasives, hardness of the bond, C is hardness of the bond, D is ability of the grinding wheel to penetrate to the workpiece. Hardness of grinding wheel is determined by, option A is hardness of abrasive grains. No, it is not. Option B is ability of the bond to retain the abrasives. It may be. C is hardness of the bond. This is also not. D is ability of the grinding wheel to penetrate the workpiece. This is also not. So 42 answer is ability of the bond to retain abrasives. Ability of the bond to retain abrasives. So answer is B. Next question is question number 41. Trepanning is performed for. So trepanning is also called producing a hole, one of the process. Generally we know that for producing hole we use drilling. But question number 41, gate 2002. Question number is trepanning is performed for option A, finishing a drilled hole, option B, producing a large hole without drilling, option C, turning a hole for alignment, option D, enlarging a drilled hole. Trepanning. So trepanning is performed, he has mentioned, first option is finishing a drilled hole. So finishing a drilled hole is not trepanning, it is reaming. So answer A is not. Answer B, producing a large hole without drilling. It may be right. We will see other two options. Option C is turning a hole for alignment. This is not. Option D is enlarging a drilled hole. Enlarging a drilled hole is counter boring or counter sinking. So option D is not. So option B is correct. Here for producing a large hole without drilling. Trepanning is performed for producing a large hole without drilling. So answer is option B. Question number 3940, linked answer question. ME 2003, 4 marks question. So here a cylinder is turned on a lathe with orthogonal machining principle. Spindle rotates at 200 rpm. The axial feed rate is 0.25 mm per revolution. Depth of cut is 0.4 mm. The rake angle is 10 degrees. In the analysis, it is found that the shear angle is 27.75. Calculate the thickness of the chip produced. So data he has given is orthogonal turning, on lathe, spindle rotation of the speed of the spindle, n equal to 200 rpm, the axial feed rate f equal to 0.25 mm per revolution, depth of cut 0.4 mm, rake angle alpha equal to 10 degrees. In the above analysis, the shear angle is 27. Shear angle, we general our notation is pi, 75 degrees. First question is 39 question is the thickness of the chip. Thickness of chip produced. Options are A 0.511 mm, B 0.528 mm, very close, C 0.818 mm, D 0.846 mm. So this is the one, the thickness of the chip produced, T2. So from this, how we have to calculate? So we don't know T1, we don't know, he has given depth of cut. Okay. So for this solution is in orthogonal turning, the speed he has given, the depth of cut. Depth of cut is nothing but uncut chip thickness. So that one we have to remember. Depth of cut is always uncut chip thickness. So answer is T1 by T2 is always less than 1. So answer definitely will be near to the 1. So option C or D is the correct, but anyway we will solve. Uncut chip thickness. Sometimes indirectly they give as depth of cut. Depth equal to depth of cut equal to T1 0.4 mm. So from this we know we have to calculate chip thickness ratio. Okay. So substitute tan pi, we know tan pi equal to r cos alpha by 1 minus r sin alpha. Tan pi, tan 27.75 equal to r cos 10 divided by 1 minus r sin 10. So substitute the all values and simplify or calculate r value. R equal to the number you will get. R is T1 by T2 equal to the particular number. Okay. This is one method. I will tell you another method. So we need T2 equal to T1 by that amount is equal to, the answer is 0.818 mm. So there is another method is chip thickness ratio. T1 by T2 equal to sin pi by cos pi minus alpha. Substitute here. So we need T2 equal to T1 cos pi minus alpha divided by sin pi. So T2 equal to T1 we got 0.4, cos pi is 27.75 minus 10 divided by sin 27.75. Substituting T2 equal to, directly you will get 0.818 mm. So answer is C. Simple, but only thing is you need to know which formula you have to use when. So if you remember that practice, if you practice the problems, then it is easy. Next, question number 40. So it is also linked to the above one. In the above problem, the coefficient of friction at the chip tool interface was obtained using Ernst-Marchand theory. So by Marchand circle theory, the coefficient of friction at chip tool interface is how much? Answer A is 0.18, B is 0.36, C is 0.71, D is 0.908. It's a multiple of 18. He has given 18 to the 36, 18 4 the 72 nearly, 18 5 are 90. So options are very logically as given. You have to be careful. Answer. How to solve this? So based on Merchant's theory, you know that from Merchant's theory 2 pi plus beta minus alpha equal to 90, where pi is the shear angle. He has given pi 27.75. Beta is friction angle. Beta we need to calculate. Minus alpha is 10 degrees equal to 90. From the above, beta equal to the value whatever we get is 45.5 degrees. So coefficient of friction, beta equal to friction angle, coefficient of friction mu equal to tan beta, that is equal to tan 45.5. the value is equal to 0.98. Out of this, the closest answer is D. So in exactly sometimes you may get closest answers, so that's why closest answer is D. Question number 36. Quality screw threads is obtained by GATE 2003. If you look at 2003, how many questions he has asked? 6, 7, 8 questions, 8 marks questions. This is old format, but at least in now format they will ask 5 questions. Quality screw threads are produced by So option A is thread milling, option B is thread chasing, option C is thread cutting, option A is thread milling, option B is thread chasing, option C is thread cutting, with single point cutting tool. Option D is thread casting. So answer for the above problem is 36 question. Answer is thread chasing, B. Next topic is measurement of tool tip temperature. Methods of measuring tool tip temperature. So methods of measuring tool tip temperature. First one is tool work thermocouple. Thermocouple, we know what is a thermocouple. Thermocouple is used temperature measurement. Calorimetric setup. calorimetric setup. 3 is pyrometer. So these three are the temperature measuring equipments used to discuss how we measure with these equipments and when we need to use those particular applications. This they ask generally theory questions. First one is tool work thermocouple. First one is tool work thermocouple. The thermocouple is formed by joining two wires made by different materials. Thermocouple. So let us take a tool. Side view will be this one, single point cutting tool. So this is the tip of the tool. So this point you need to measure the temperature. So use the thermocouple, keep attached to that, near to that. So this is the thermocouple where it will show voltage readings for particular. Here this is the T2 tool tip temperature, this is T1. T1 is room temperature. So the difference between the temperatures at the two ends of the thermocouple is shown as a voltage difference. So voltage, it will show a reading. So T1 is room temperature, T2 is tool tip temperature, approximately you will get the value. V is voltage difference, or potential difference. So the two wires are made by different materials, joined them at their ends, and the two different temperatures are maintained at two junctions. The EMF generated in the circuit which is flowing through and is proportional to the temperature difference between the junctions. If two wires are made by two different materials, joined them together at their ends. If you look at the diagram, this is one end, this is one end. So at their ends we are joining the two wires, wire A and wire B. Okay, so at the join there at the ends, the two different temperatures are maintained. Two different temperatures are maintained at two junctions, obviously. At two junctions. So because of difference in temperature, the EMF, which is potential difference, electromotive force, is generated due to in the circuit due to which is flowing through it, due to temperature difference between the two junctions. So voltage V is potential difference EMF is V directly proportional to the T2 minus T1. So thermocouples can be used measurement of temperatures up to 800 accurately. Thermocouples can be used to measure the temperatures up to 800 degrees centigrade accurately. After this, because it can't, and beyond it also is possible, but the thermocouple reading is error will be there. Sorry. Beyond this, error will increase. Error in measurement will be large. Machining of normal materials temperature will be above 500, whereas during machining of titanium alloys the temperature is such comes measurement of temperature above 800. Machining can be done by pyrometer, optical pyrometer, or disappearing filament type of pyrometer. So temperature pyrometer that we discuss. The potential difference here is how to measure, how we will get potential difference is, so whenever the difference, suppose if it is the difference between the temperatures is 100 degrees centigrade, T1 and T2 difference is 100 degrees centigrade, the voltage reading shows 5 reading like 5 mm or something, 5 degrees. That means for each degree 20 degree temperature, 10 degree temperature, the rotation of voltage meter, there is the standard value will be there for 1 point rotation or 1 degree rotation. Instead of degree, you can, it's like our time clock, one reading how much is the temperature difference. So if the voltmeter is showing 5 points, 5 that is reading 5, that means the temperature difference is 5 into 20, 100 degrees. So based on the voltmeter reading, we have to calculate the temperature difference developed. So next method is pyro method. So pyrometer is, the purpose is to measure high temperatures, very high temperatures above 800 degrees centigrade. So temperatures, actually we are using